So we want to study the stability of the origin of this system. We are assuming that f of 0 is 0, so the origin is an equilibrium point, and we want to study the stability of the origin. Okay? What the results that apply to the origin apply to any equilibrium point, isolated equilibrium point. So what we do, if we are able to find a state function, that is to say, a function that maps each value of the state to a real number, I call it V of x. Okay, so for any x, for any state, I have a function V, which is a real number. And this function is positive definite. What is a positive definite function? Well, at the origin of the state space, it's 0. And away from the states, from the origin, it is always positive. And it's continuous with first partial derivatives that are continuous. Then, if you are able to find this function in a region around the origin, then if I'm able to prove that the derivative, the total derivative of V with respect to time along the trajectories of the state of this system is smaller or equal to 0, then the origin is stable, at least. It is asymptotically stable if instead of having smaller or equal, I have a strict inequality, that is to say, if dVdt is smaller than 0. And we mentioned a geometrical interpretation. So in the case of a plane, so I have x1 and x2, that's the state variables. And I consider a trajectory that starts at some initial condition. Okay? And for each point in this trajectory, I can compute the corresponding value of this V function. Okay, this is a Lyapunov function if V is decreasing along these trajectories for any trajectory. So this V should be decreasing whatever the x0 might be. So if I consider another one here, it should also be decreasing. So on. Okay, and if V is decreasing, this means that x is approaching the origin, or at least not escaping away. So this V that satisfies these conditions, that is to say, a positive definite function and a function which is decreasing along the trajectories or non-increasing along the trajectories of the system, only decreasing because we have dVdt is smaller or equal to 0, then this is called a Lyapunov function. If you can find a Lyapunov function, then the origin is stable. If this inequality is strict, that is to say, smaller than 0, then it's more than stable, it's asymptotically stable. Okay, that's the criteria. Now, the difficulty is finding V. Okay, it's finding V. In some cases, we know how to find some V's. I will give you some examples in a moment. How can we compute this derivative? We should use the basic rules for derivatives, because what happens? V depends on x and x depends on t. So we use the so-called Kane rule for differentiating the composite function. This means that the total derivative of V with respect to time is the sum of the partial derivatives of V with respect to the components of x times the derivatives of x, of the components of x with respect to time. Okay, this is the Kane rule for derivatives. In Portuguese, it's a derivação da função composta. Okay, so V depends on time through x, so you have to differentiate with respect to x, and then differentiate x with respect to t. This is something that you have certainly studied and most probably forgotten in the first years of when you did your degree some years ago.
Yes.
Okay. Now, I can compute this dx dt because each dx dt is an f. Okay, so I can compute dv dt by using this expression. So it's dv dx1 f1 plus dv dx2 f2 and so on. Okay, remember that this f is a vector with as many components as x, because the x it is also a vector. So we have here f1, f2, etc. Okay, so to compute the derivative, you use dv dx1 and then use f1 for dx1 dt, as in the next slide. So you use this formula here within the square. Let's see one example. Let's see one example. Suppose that you have this, suppose that you have this function, this system. And the origin is an equilibrium point, because if you make x1 equal to 0 and x2 equal to 0, these derivatives vanish. Now let's study whether the equilibrium is stable or asymptotically stable. So I try a quadratic function on x1 and x2. I try x1 squared plus x2 squared. This is a trial. And well, this is positive definite, because if x1 and x2 are 0, you get 0. 0 squared plus 0 squared is 0. And if x is away from 0, you get a positive number, because you are summing numbers that are squares. So they are positive. So this is positive definite. So we must check whether v decreases along the trajectories of this system. For that, I'm going to compute dv dt using that technique and show that it's always negative. So remember that v is x1 squared plus x2 squared. So dv dt is the derivative of x1 squared, which is 2x1, times the derivative of x1 with respect to t, plus the derivative of x2 squared, which is 2x squared, times the derivative of x2 with respect to t. Now, I use the expressions for x1 and x2, for the derivatives of x1 and x2, which are given here. So I plug these expressions here and here. And then I try to cancel out things. And what do I get? I get minus 2 x1 squared plus x2 squared plus x1 squared, x2 squared. And for x different from the origin, this is a sum of squares, and it will always be positive. So with a minus sign, it will always be negative. So you can say that this is always negative for x different from 0. And the conclusion is that x equal to 0 is a equilibrium, a asymptotically stable equilibrium point. So the technique is very simple. The big difficulty is to find an f. Okay? In many simple problems, you just try to build quadratic functions. Then there are classes of problems for which you can prove systematically, or you can obtain systematically v. There are some methods for classes of problems, but there is no general problem. Okay? There is no general method to find a v. The fact that you don't find a v doesn't mean that the point is asymptotically stable or not. It just means that you don't know. Any question?
No.
Okay, so in this example, what do we have? If you plot the contour levels of V, you get circumferences, okay? And this is one trajectory. This is actually the trajectory is of that state is, it does not turn so much, but okay, assume it's a trajectory. What happens? You have just proven that along this trajectory, V is decreasing, so you are always going to smaller values of F, you are cutting these level curves to the inside. So you are approaching the origin, okay? Since V is decreasing and the minimum is at 0, you are approaching 0. That's the essence of the method. So you are used to measure distances in meters or yards or I don't know. In Portuguese, there are some ancient units.
Excuse me, so in your slides that you put that the C2 is bigger than C1 and again C2 is bigger than C2, this one I don't understand. Oh, this is a mistake, I think. Sorry.
These circles correspond to constant value for, it's a local, is the set of x1 and x2 points, of points with coordinates x1 and x2, such that V is constant. Now, if you have x1 squared plus x2 squared equal to a constant, this defines a circle.
Oh, okay.
Okay.
But in your slides, I think you made a mistake. So
here.
Yes, like C2 is bigger than C, so it must be C3, I think.
C1 is smaller than C2 because it's inner than C2, and C2 is inner smaller than C3.
Okay.
Corresponds to different values, smaller and smaller values. Okay. Look. If you equate this to, say, C1,
okay,
that defines a circumference.
Oh yeah.
Of radius square root of C1.
Yes, I understand this.
Okay. Now, the smaller the circumference, okay, the smaller the value, the smaller C. So C1 is smaller than C2 because it's inside. And so this is like this. This is coherent with this sequence. Was that your question?
Yeah, I got it now.
You understand it now?
Yeah, I understand that. I only wanted to mention in your slides you made like put it like C2 two times. That's why
yes, okay, C2 two times. This C3.
Yeah.
Okay, this should be C3. Thank you. Okay, this should be C3. But the important thing here is you are cutting these circles inside. So you are decreasing. You are approaching 0. Okay?
But it will approach to the 0 or no? Never approach to the 0 in this case.
If the derivative of V is negative, strictly negative, you are always decreasing, so you approach 0.
Okay.
If it is smaller or equal to 0, then you can wonder. You can have something which is periodic solution or something like that. Okay?
Thank you.
So you no longer have the warranty that you go to 0.
Oh.
Actually, the proof of the method is what I'm saying, but the idea is this one. Then you need to formalize it. We're not going to make the proof, but intuitively, you see that if V is always decreasing along the trajectories, you are always going to smaller values of V. That is to say, you are approaching the origin. If you have smaller or equal to 0, you may be kept sometimes at the same distance, then you go again, and so on. Okay. Now, this is a simple case. You can have more complicated equations with more states. It's impossible to visualize. More questions? Okay. Let's actually these are the solutions. Okay, these are the solutions. So let's see if you are able to solve a problem. Okay. I want to prove that the origin is an equilibrium point, is asymptotically stable or at least stable equilibrium point for this system of equations. And I tried this family of candidate Lyapunov functions, where A and B, they must be positive. You can select them in a convenient way. So try, well, this is always, provided that A and B are positive, this is always positive for x1 and x2 different from 0. Now you have to compute the derivative and see what happens. So try to do it. Remember that the derivative is partial derivative of v with respect to x1 times dx1 dt, but then dx1 dt is this expression, plus partial derivative of v with respect to x2 times this expression. So try to solve it. To compute these derivatives. Please copy this because I'm going to the whiteboard. And my tentative B. So V depends on time through x1 and x2. So you have to differentiate v with respect to x1 and multiply by the derivative of x1 with respect to time plus v with respect to x2 and multiply by the dependency or the derivative of x2 with respect to time. Have you done it?
No.
So this is what? This is what? What shall I write here?
AX1.
A? What? Okay, let me start from the beginning. So this is the, I mean, what do you obtain from, what is the expression that allow you to compute that? Is
dv dx1.
dv dx1 and then
dx1 dt.
times dx1 dt. This is a partial derivative and this is a total derivative plus what?
dv dx2 times dx2 dt.
And this is what? So dv dx1 is what?
AX1.
This here is a x1 and dv dx2?
It's bx2.
Bx2. Okay, so this becomes a x1 and then dx1 dt. Where can I get it?
x1 dot.
Yes.
x1 dot, and x1 dot is
Minus x
minus
to the power of 3
x3
plus
plus
x1
x1 x2 squared plus the other term. And the other term is b x2 and then
minus 2 x1 squared
to x1 squared
x2
x2
minus x2 cube.
Okay, now we simplify this and what we get?
A parenthesis.
Parenthesis. Why parenthesis?
No.
Okay, but
Will you
let's
not?
put on.
Will you not multiply x1?
It would be minus ax1
minus a
x1 power 4.
And then
So would be like again would be plus ax
Okay.
plus
Okay.
ax2
a what?
ax1
x to 1.
Yeah, x1 square.
x1 squared. You want to multiply
ax1
by that one,
square.
so
Yeah, ax2 square too.
x2 squared.
Yeah. And plus. No, sorry. I think because again it would be like minus b minus bx minus 2bx minus 2bx
minus
yeah 2
2b
x x1 square, so, and x2 square, and minus b x2 power 4.
Okay.
Is it right? So, is it correct?
Yes.
And now we have to decide what are the values of A and B. So what do you think could be a choice for A and B?
So first, I think we should simplify.
We should simplify things. So this is what?
I was in the middle, so
If we will put x, if we put x a x1 squared
ax1 squared.
outside.
I want to have something which is minus the sum of even powers, menos uma soma de potências pares. Okay? Because if I have an even power, I have, say, x1 to 2 or x1 to 4, I know this is positive. So I don't want to have even, I don't want to break it in products. So I have this term here.
So can we put like parentheses a minus 2b multiply multiply x1 power 2 x1 square x2 square. So we would like to take minus 2b
minus 2b
in parentheses. So
x1 squared,
x1
x2 squared. And then we have the rest. So
then,
this is this terms in the middle, minus a x1 squared, x1 4, sorry.
Yeah, 4.
Minus b x2 fourths. So nice choice of A and B. They should be positive because this should be bigger than 0 for x1, x2, different from 0, 0. Okay? Away from the origin, this should be positive. So this implies that A and B should be positive. Otherwise, you can have, if one is positive and the other is negative, then you can find values for which this vanishes. So one possible choice is what?
A1 and B 0.5.
A1 and B 0.5. And then what happens?
The first term disappears. And
this term here. And you have, and this becomes minus x1 fourth plus 0.5 x2 fourth between parentheses. Okay, so this is a negative of an even power, an even sum of powers, and this is always what you say, what you think.
Negative.
Always strictly smaller than 0. Okay.
So can we give any value to the A and B in this term?
Yes, because what is important is to find one Lyapunov function.
Oh, okay.
Okay? One Lyapunov function. So select A and B, and the derivative becomes strictly negative. the original function was strictly positive, constant, differentiable. So what is the conclusion about the stability properties of the origin?
It is asymptotically stable.
It is asymptotically stable, okay? So let's see another example. Let's see another example. Okay, if you want to see this is obtained by numerical integrating the equations for different. Sorry. This is the numerical integration of the system of equations for different initial conditions, you see, and all the trajectories go to zero. So it's asymptotically stable. I mean, if you disturb it a little bit, you return. Okay, so let's see another example. Let's also, I will return here. Maybe I have something. Oops, no. Sorry, I will try to find a more interesting example. Maybe I have it here. Good Lord, I don't have it. Okay. Let's study this case, the pendulum. Okay, if you apply the equations of a pendulum, it's a so-called mathematical pendulum. No friction. So x1 is this angle theta. X2 is the derivative of theta, is the angular velocity. So the derivative of x1 is x2, and the derivative of x2 is the angular velocity, and the angular velocity verifies this, right? Okay. And we use as candidate Lyapunov function, this function here. So x in this case is a scalar. So g and L are constants. G is the acceleration of gravity acceleration, and L is the length of the pendulum. And I try with the Lyapunov function, which is the sum of potential and kinetic energies. Okay, so this is the potential energy, is basically the energy that you need to rise this mass for this distance. That's why it appears this term 1 minus cosine of x1 minus cosine of the angle. And this is the kinetic energy, which is the rotation. Okay, so you have here the square root of the angular velocity. So let's believe this is correct. You don't have to give an interpretation to the Lyapunov function. Now, for what are the equilibrium points? So x1 equal to 0, x1 equal to 0 is an equilibrium point, and x2 equal to 0. So x1 means the pendulum down because the angle is 0 and the velocity is 0. You have the pendulum here. You have your you have your pendulum down. Okay. What is your feeling about stability of this equilibrium point? Stable, unstable, asymptotically stable. No friction.
But
Asymptotically stable?
Yes.
So if you have no friction, it starts, it never ends.
Yeah.
Okay. So
but it always returns to 0.
No, it does not return to 0 because it's not, you don't have any friction. So you are always changing potential energy by kinetic energy and so on. Maximum of potential energy, maximum of kinetic energy, maximum of potential energy, and so on. You don't dissipate energy if you have no friction. Okay, so you never return to the origin.
But also no friction and no gravity. You mean also by the gravity?
No, I have gravity. This is subject to gravity. So it's gravity that makes this term. Okay, that's why you have this. That's why you have this term here, G over L. It's because you are assuming that you have the force of gravity. So you decompose the force of gravity in two components. One is along the L that stretches the pendulum, and the other is tangent to the movement that makes it accelerates. Okay? So gravity, but no friction. If you have no friction,
yeah, it will continue.
By energy, so I expect this to be full.
Yeah, forever. Yeah.
Never ends. Okay, it does not exist in physical terms, but that's why it's called a mathematical pendulum. Okay, so we are expecting this to be asymptotically stable. Okay, so let's try to solve this problem first with the method of computing the eigenvalues. Okay, to see what happens. So this is not a nonlinear equation because you have the sign here. So remember that you have to compute. Let's go to the whiteboard that we can write it. So x1 dot is x2, and x2 dot is minus g divided by L sine of x1. So let me write equations here. x1 dot is equal to x2, and x2 dot is equals to minus g divided by L sine of x2. So 0, 0 is an equilibrium point. No? 0 0 is an equilibrium point. And you remember we should compute df1 dx1, df1 dx2, df2 dx1, df2 dx2. You should compute this matrix for x equals to the equilibrium point. Okay? So let's see. Let's set, and then you compute the eigenvalues. So compute this, compute the eigenvalues. Let's put a number. So to simplify things, I assume G is 9.8. So I just put a 10, that corresponds to L equal to 1 meter. So minus 10. So compute the matrix. When you have the matrix, raise your hand so that I can see. I mean, your informatic hand, you don't need to do like this. What is F1?
x2
And F2?
minus 10 sine of x2.
Okay. First row, who tells me the first row?
0, 1.
0 and 1. Good. And
I didn't calculate the other, so I had to go quickly.
And here, df2 dx1?
Minus 10 cosine of x1.
df2 dx1. This should be 1. Sorry, this should be 1. But df2 dx2?
0.
0. And here, what is the derivative of the sine?
Cosine.
Cosine. So this is minus 10 cosine of x1. Now, we are computing this for 0, 0. So this gives you what? Well, 0 is always 0, 1 is always 1, and the cosine of 0.
1.
1, so this is minus 10. And this is a difficult question.
0.
0. Now compute the eigenvalues. So what are the eigenvalues? It's a number such that if you square it, you get minus 10.
Plus minus square root of 10 I.
Plus or minus j square root of
Oh,
10.
yeah, J.
Good. Well, okay. That's J is the electrical engineer style. Okay, that's the square root of minus 1. So we have the eigenvalues. If this is the C-plane, where do I have it?
In the imaginary axis.
One here and one here. So what is the conclusion about stability of the nonlinear pendulum about the down position?
We can't conclude anything.
We can't conclude anything because the eigenvalues are over the imaginary axis. No conclusion. Okay, no conclusion. Okay. Now, any question about this example?
No.
So let's try now to use our new method, Lyapunov method. So this was the method based on linearization, no conclusion. Now let's apply Lyapunov method. And if we apply the Lyapunov method, let's try to use this function. Now, okay, let's assume it's positive. If x1, the cosine is always smaller, no? For x1 equal to x1 equal to here, it's pi. Equal to 0, because I'm counting the angle in that way. So for cosine equal to 0, what is the cosine of 0?
1.
1. So you have 1 minus 1, this is 0. And velocity is 0, this term also vanishes. So in the down position, the v of x, v of 0, 0 is 0. And then cosine gets smaller than 1, so this is positive, and this is a square, so this is always a positive function. Okay? At least locally. At least locally. Remember that this is periodic. But locally, close to x1 and x2, this v is something from which you can drink water or beer or tea, depending on your favorite. Maxi would take tea, probably also café. No, in Iran you have special type of tea, no, but
Yeah.
it's also a tea region. Indian tea is different from Persian tea.
Yeah.
Okay, now we have the problem of computing the derivative of v a long time. So try to compute the derivative of t a long time. So what you have to compute, you have to compute the partial derivative of v with respect to x1 times x1 dot, it's here, x1 dot, plus the partial derivative of v with respect to x2 times x2 dot, it's here. So try to compute this derivative and simplify the expression to see what happens. When you get the result, raise your hand, please. So it's the partial derivative with respect to x1 times x1 dot was the partial derivative with respect to x2 times x2 dot. When you finish, raise your hand. It's on. There must be some. How can you share it? Oh. Oh, invite more. These things, sometimes we see the reactions, sometimes we don't see the reactions. So, what is the conclusion? Have you done it, Maxi?
Yes.
And what is the result?
0.
0. So, it is 0.
Yes.
What is the interpretation? What can you conclude something about with this function about the stability properties of 0, 0? If the derivative is 0,
it will go to the 0.
So what does the theorem says? The theorem says, let's go to the theorem. That if dvdt is smaller or equal to 0, then you can say that the origin is stable. If it is strictly 0, it's asymptotically stable. If it is smaller or equal to 0, it's stable. Otherwise, you can't say nothing.
So then it's asymptotically stable.
Is asymptotically stable? So dvdt equal to 0 allow you to say that it is asymptotically stable?
No.
Who said no? Café?
It's stable, I think, yeah.
No, but it's stable. Yeah, it's stable.
It's stable.
Stable.
Yeah, stable.
So, in which case are we?
No, it's stable.
In this case here,
yeah.
dvdt equal to 0 is equal to 0 is logically the same as smaller or equal to 0. It's 0, always 0. Okay. So we reach the conclusion. Okay. The linearization could not tell you anything, but this tells you that it is stable. And that's the idea that it oscillates. Actually tells you that it is stable at least. Okay. It could be asymptotically stable, but at least it tells you that it is at least stable. In our intuition tells you that it's going back and forth without stopping, no dissipation, so you never go to the origin. Okay, so this example is an example in which the method based on linearization could not give you any result, but the method based on the direct method of Lyapunov gave you a result. Okay. No. Now let me confuse you a little bit. So if you compute this derivative, you get 0, always 0. But if it is always 0 for any state, it is 0 when you have this down state, but it's also 0 when you have the upper state. So you are proving that the pendulum in the upper position is stable, and we know it's not stable. Okay, we know it's not stable because if you disturb it a little bit, it will fall down. That's what our intuition tells us. So what is the problem here? The problem is that V is no longer definite positive there. If you plot V, if you plot the energy, locally is something, locally around 0, 0, you see, it's something which is a positive definite function. But if you plot it around x1 close equal to pi, pi is pi radians, and 0 velocity, then it's a saddle point, you see. It's not positive definite function, okay? So V is no longer positive definite, okay? V must be, for you to apply the result, V must be a positive definite function, and it is not a positive definite function when you are considering the other equilibrium point. So for the point at pi 0, you can't take any conclusion here. The derivative is 0, but V is no longer a Lyapunov function. Okay? Actually, you have an infinite number of stable equilibrium points, and unstable equilibrium points. You have this nice plot just for 3 equilibrium points, 3 stable and 3 unstable equilibrium points. Okay, and if you look at the trajectories, what you have around 0, 0, you have something that is turning around. Now, this point here is the upper position. So if you deviate a little bit, either you go that side or you go this side. Okay? So the arrows tells you, the arrows are the field defined by the equations, the sense of derivatives. Questions?
No.
Okay. We also have another theorem. So the theorem based on derivatives comes from, say, 1865 or something like that. Then after 30 years, you have Lyapunov theorem. And then in the 50s of the 20th century, so about 60 years after Lyapunov, you have this invariant set theorem. Okay. Now, suppose that you come to the conclusion that your dVdt is smaller or equal to 0. Can you say something more? Can you say something more? Okay, and this something more is the invariant set theorem. Now, let's see if we can have some intuition about this theorem. Your V is decreasing. Okay, your V is decreasing, and your V is a kind of distance to the origin. So when X is evolving, V is decreasing. But then the V stops decreasing. That's when the dVdt is 0. Okay? So suppose that you are in a situation in which dVdt is 0, is smaller or equal to 0. Okay? When do you stop? That is to say, where are you going to? Can you characterize the set of points where you are going to? If you are always decreasing, if dVdt is smaller than 0, you go to the origin. Do you have any intuition or any hint? Okay, where to the set of states where you go when you are in this situation that dVdt is smaller or equal to 0?
Well, we will go to the zero. So
Sorry, I cannot understand you.
it will go to the zero, toward to the zero. So if it is a smaller,
It will probably not go to the zero. It will stop before the zero. Because if for sure it was going to the zero state, to the origin of states, it would be asymptotically stable, and we know it is not. It may not be asymptotically stable. So there are some states around the 0, 0 to which you go. Can you say something about this set of states? So if you go to look at this plot, you have the origin there in the middle, but probably you will be approaching some sets around this. Can you say something about this set?
Yes, it's infinity. I don't know.
Oh,
Infinity?
okay.
So it is. I don't know. Like,
probably it's not infinity because I mean, for sure it's not infinity because you know that you are decreasing your state. The state becomes stable. So you are decreasing your state. Your V is decreasing, your X is decreasing. So X is not going away because V is decreasing. So X is not going to infinity for sure. So for sure it's not infinity.
I mean, you said that it would be somewhere around the origin.
The origin.
So, but this somewhere could be anywhere. So that's why I said so. It would be
but
like.
Can you say something about this region where you go? Don't you have any hint? Because what makes V change is the fact that the derivative is decreasing, no? So that we have a temptation to say something. No ideas?
So it should go like close, very close to zero without never reaching it.
No, because it would be symptotically stable. It can go to a wider region. No. When your state evolves, your V is decreasing.
Yes.
Okay, because you know that dVdt is smaller or equal to 0. When does it stop?
When it's equal to 0?
When dVdt is equal to 0. So one temptation is to say that the set where you go is a set where dVdt is equal to 0. That's a temptation, but it's wrong. Okay? Our intuition tells that, but intuition is wrong. It's more stringent than that. Is the largest invariant set inside this region. What is an invariant set? What is an invariant set? Let's define an invariant set. An invariant set is, suppose that you have your system of differential equations and you integrate the differential equations starting on an invariant set, you stay on it. Okay? So an invariant set is a set of states such that if you have the initial condition inside the state, you never leave the state. You never go away from the state, go out of the set. Okay? For instance, an equilibrium point is an invariant set. Because if you are at an equilibrium point, you stay there. The whole space is an invariant set because you never go out of the whole space. A periodic solution corresponds to an invariant set because you are always in this region. It's a closed curve. Okay, that's the notion of invariant set. If you start there, you stay there. Okay. Now, the theorem of the invariant set says, suppose there are some technicalities, but let's forget these technicalities at least for the moment. Suppose that you come to the conclusion that dVdt is smaller or equal to 0. Then you can say that all state trajectories approach the largest invariant set in which dvdt is equal to 0. It's written here. Okay, so you compute this set of states, dvdt, such that dvdt is 0. This defines a set of states. And then you have to find out the largest invariant set. It looks a bit funny, but let's see an example. Okay, so this example. Suppose that I suggest you this V. So compute V dot. Compute V dot. So remember that V dot is dv dx1 times x1 dot plus dv dx2 times x2 dot. And try to conclude to say what you can conclude about the equilibrium point, the stability properties of the equilibrium point with the standard Lyapunov function, the Lyapunov theorem. I will go to the Did I have the 1/2 here?
Yes.
Okay. So V dot is x1 dot plus x2 dot, and this is what? x1 dot is minus x14 plus 2 x1 x2 cube, and then we have x2 dot minus 2 x1 x2 cube, and this cuts with that. So you just have minus x1 fourth. So V dot is minus x1 fourth.
It is equal to 0.
Is this equal to 0? You think so?
Yeah.
Always 0? For instance, for x1 equal to 1, what is V dot? For x1 equal to 1,
So
what is the force power of 1?
So it would be like
It's 1 times 1 times 1 times 1. That gives me
1.
1. So V dot is, if you have,
minus 1, yeah. So
if you have, say x1 equal to 1, say a point here. This is minus 1. So a point here. That's an example in which you have x1 equal to 1. So you have V minus 1. Okay? And V is minus 1, and so on. So along a line here, it's minus 1. So it's not always 0.
Oh, yeah, it is
So,
like.
can I compare this with 0?
Yeah, but it is.
Could it be positive? Could it be positive?
No, I think because it is like minus, so it would be.
So it can't be positive. It can't
Yeah.
be positive.
So it would be like a smaller and
it's
minus, yeah, equal
smaller
and
or equal to 0.
equal to 0.
Okay. Outside. Can it be 0? Can it be 0?
Yeah. So if you
Where? Where?
So if you put like x to equal to 0, so it would be
x1
like,
equal to 0. So here.
So yeah, here.
This is the set of points for which x1, no?
Yeah.
v1, v dot vanishes. So this is smaller or equal to 0. So what can you say about the stability of the origin?
It's stable.
It is stable, yeah.
It is stable at least.
Yeah.
Okay. Now, this is what the standard Lyapunov theorem tells you. The invariant set theorem, tells you compute the set x such that v dot equal to 0. Okay? Then all trajectories of states, all solutions converge to the largest invariant set in this set. By this set, I mean the set where v dot is 0. Okay? And an invariant set is a set such that if I start there, I stay there. Okay, so what is the set for which v dot is 0?
x1 equal to 0.
It's this red line here.
Yeah.
Okay, so in this red line, you have v dot equal to 0. Okay?
Yeah.
So let's try to find out what is the largest invariant set. For instance, suppose that I'm here. Do I stay in this set when time evolves?
Yes.
Yeah. So why do you say yeah?
Because you're still in x1. Because x. Right?
Look at the equations. Look at the equations here. So here, what is the value of x1?
It is 0, so x1
is 0. So this term is not there. So what is the derivative of x? What is the derivative of x2? What is the derivative of x2?
0 again.
Is 0. Is 0. So if it is 0, you move in the horizontal direction because x2 is not changing. Now look here. What happens to the derivative of x1? This term is 0. What about this one?
No, it's not 0.
Not 0. Can you say something about the sign?
It's positive.
It's positive because x2 is positive. So where are you moving?
To the right.
To the right. Now, conclusion. Does this point belongs to an invariant set contained in the set where v dot is 0?
Yes, it does.
It does? You stay there?
Oh no, you move to the right, sorry.
You move to the right, so you go away, immediately go away. So it's not inside an invariant set. Okay? What about here? What happens? Where you go? What happens if you are here?
But their x1 is also 0.
So it's more or less the same. Probably you go with a different velocity to move away. So this is not. No. Now, what about here?
But it should be also to the right because x1 is also positive. It's also 0.
X1 is 0. So x2 dot is 0. So you move in the horizontal. Here, this is 0. But now x2 is negative.
Yeah,
Then you
so
move
it will
to the
go
right.
to the left.
Left.
So
The derivative is negative, so you move to the left, but you go away. So there are no points below the invariant set is empty. I mean, if you are here, where do you go?
To the left,
to
too.
the left.
To left. If you are here, where do you go?
Left.
To left. So there is no invariant set. Is that right?
Yeah.
Are we forgetting something?
Unless
The
x2 is 0, too.
origin.
The poor 0, 0.
Yeah,
What happens here?
Yeah.
What happens if you start here?
Then it stays there.
They will stay there. So this is the largest invariant set contained in the set where v dot is 0. So what is the conclusion from this theory?
As you said, it is like equal to 0. So it will be like equal to 0 as the minus.
So what is the conclusion about the trajectories of the solutions of the differential equation? They appear, all of them converge, all of the trajectories converge to the largest invariant set inside the set where v dot is 0. So here in this case, all trajectories converge to where?
To the origin.
The origin.
The origin, because the origin is the largest invariant set, you see. Okay? Okay, so you can apply differentiation to this, you don't get any result. Then you apply Lyapunov theorem 30 years after, and you conclude convergence, stability at least. And more 60 years, okay, and you are able to prove that actually it's asymptotically stable. But you need that invariant set theorem. Okay? Now, this invariant set is not, actually it's quite important, for instance, in robotics and control. We are not going to explore that, but we can design, for instance, adaptive controllers with this, taking advantage of this invariant set. So this is not just a theoretical toy. It's quite important to design controllers and even adaptive controllers. So controllers in which you adapt some suppose that you don't know some parameter of the system, and you design an adjustment law of this parameter such that in the wall we have a Lyapunov function, and then you use this invariant set theorem to give conditions for this the output of the system to track the designed reference. Okay, so we are not going to see that, but bear in mind that we have this. It's a really one of the most important tools in control, nonlinear control, modern. These ideas actually came initially in the end of the 60s. A guy called Marx was the first one to have this for linear systems. But now it's, I mean, you pick up a book or a paper on nonlinear control of drones or aircraft or robots, and it's full of, or underwater vehicles, and it's full of these arguments based on this invariant set theorem. Okay, so we have really seen three quite important tools to study stability: linearization, which is, it does not cover everything, but in many cases it's quite useful. Lyapunov direct theorem, direct method, and now this invariant set theorem or LaSalle theorem. LaSalle was this was the original version was from LaSalle. LaSalle was not French, was an American electrical engineer. It's a funny thing. He was not a mathematician. He was an engineer. Okay, questions?
No.
Now, you are in condition to solve series number 3, which is quite small. So in 1 hour or maybe less than 1 hour, you are able to solve it. It's just some problems, no simulations, just simple computations about stability using these ideas. Okay?
Okay.
So have a nice weekend. We see
You
each
too.
other on Monday.
Yeah, you too. Thank you. See you.
Okay, thank you
Bye.
very much. Thank you. Bye.